Okay, good morning, everyone. Welcome to this platform. Of course, this is the mentor Hamburg Lehman. Today we shall be looking at this science paper 1 paper, of course, which was written on 5th August 2025. And then we shall be able to explain as many concepts as we can to simplify everything. This is a very simple paper. And of course, I know if you are seeing it for the first time, you might have certain challenges, especially in solving certain questions. But I want you to find this paper interesting and helpful. Okay. So, of course, science paper 1 is actually physics. And then I'm going to help you solve each question with a simple concept. The learner measured the diameter of a test tube and obtained, so this is what the learner obtained, 1.5 multiplied by 10 to the power negative 1 millimeters. Then they say, what is the value obtained in decimal? So the first thing you can work out is this, because you know that 10 to the power negative 1 is the same as 1 over 10. So this is just the same as 0.1. So you are just multiplying 1.5 multiplied by 0.1. So 1.5 multiplied by 0.1, you are getting 0.15 millimeters. And that makes your answer become A. Okay? Basically, that is how they found that answer. Go to the second question. Okay, the second question is saying a car traveling at 10 meters per second increases velocity to 30 meters per second in 5 seconds. What is the acceleration? So it was traveling at 10 meters per second. So you can say this is going to be your initial acceleration, which is going to be 10 meters per second. And of course, this is going to be your v final, which is going to be 30 meters per second. Then they give you the time. The time is actually 5.0 seconds. Then they are asking you to find the acceleration. Acceleration is given by v final minus v initial over the time. So acceleration is going to equal to your v final was 30 minus your initial was 10 over your time is 5. So your acceleration is going to equal to, is going to be 20 over 5. Then we're going to have acceleration is equal to 4 meters per second. So of course, this is how you're going to find your answer as A. Okay. We go to the third question. The displacement time graph shows the motion of a cyclist. Okay, cyclist. What was the speed of the cyclist at time 4 seconds? So we can make an imagination that 4 seconds is actually here. Okay, 4 seconds is actually here. Then they tell us that they want us to calculate the speed of the cyclist at these 4 seconds. But I want you to take note of something. You can actually find the speed at 5 seconds first. We know that speed, or let me just write the speed is actually equal to the distance over the time, because speed is measured in meters per second from the units. Now, what we have is actually a 5 here. And then what we have here is the distance, which is 5. Also at this point. So let's try to use that. So the speed is going to equal to, the distance there was 5. The time there was this 5 meters, of course. The speed was 5, of course, seconds. Notice that the speed that we're going to find, let me use V to prevent confusion, because this looks like a 5. So this is going to be 1.0 meters per second. Now, the speed at this particular point is also the speed at this point. Okay? At the same time, it is also the speed at this point. It is also the speed at this point. So the speed is going to remain constant. Okay, the speed is going to remain constant. So whatever you're going to find at this particular point is going to be the answer. Even the speed at 4 seconds, at 3 seconds, will still be 1.0 meters per second. Okay, so the speed will remain constant. Okay, that is provided the acceleration is changing. So of course, that is how you're going to find your 1 meters per second. The energy output of a generator depends on its efficiency and the energy output. Which set of values is correct? Okay, it depends on its energy output and its. Okay, so basically, we know that efficiency is just energy output, over the same energy which you are generating in, or energy input. Okay, so now you need to test the values. If you test the values, this is your energy input, this is your energy output. So basically, we just want to, when we divide the two numbers, we must be able to get a correct efficiency. So if you are dividing 25 by 50, are you going to get, so 25 divided by 50, are you going to get 0.1? No, it's given as 0.5. So this one is wrong. We go to the next one. If you divide 6 by 30, are you going to get 0.2? If you divide 6 by 30, you're going to get 0.2. Yes. Okay, so this one was wrong. This one is correct. Okay, and of course, this one will also be wrong. This will also be wrong because we only have one answer. So if you divide 6 by 30, you're going to get 0.2. And that is exactly what they wanted. So here you're just dividing your 6 over your 30, then you're getting your 0.3. Just wanted you to test which value you are going to get. And that is basically what you do also in the exam. You test. The next question. A crane lifts a 600 kg mass. So from our data, we have the mass of 600 kg. Okay? Through a height, so the height is actually 12 meters. Then the time is 18 seconds. Then they say, what is the useful power output? Now, power is equal to the work done over the time. But remember that work done is equal to force, okay, multiplied by distance, okay? Force multiplied by distance, that's the work done. So, we are going to test what we have. Okay. So, power is going to equal to, there we have a force multiplied by the distance over the time. Now, what we have been given is the mass. Okay, of course, the distance has been given and the time. We don't have the force. So, we are going to convert this force into something that is going to fit our data. Force is actually equal to MA, right? And because you are lifting it up, this A becomes the gravitational field force. So that's what you're going to replace here. So power is going to equal to mg, then d over your time. So now we can put in, so power is going to equal to, what is our mass? It is 600. Then what is our gravitational field force? It's 9.8. Our distance were given 12 meters over time is 18. So let's try to punch that. So this is going to be 600 multiplied by 9.8. Okay, 9.8, and then multiplied by 12. Okay, then divide by 18. Okay, so we are simply getting 3920. But I know what they did. Let me show you. So here they converted the 9.8 to 10. So you'll be using 10 meters per second for gravitational field force. Okay, at this level. Okay, so you just multiply that, divide by 18, we get a 4,000. Okay, so this is a 4,000 that we're getting. So of course our power is going to equal to 4,000 watts. Okay, we go to the next question. The next question is saying, by what process or processes is heat energy transferred from the sun to the surface of the moon? So here they're saying conduction only, conduction unless there is a solid object like a metal bar or something. Convection occurs in liquids or fluids. Radiation and convection, no? Radiation only. So of course by radiations, okay? That is how exactly energy is going to be transferred from the sun to the moon, via radiation, okay? This was actually a very simple question which does not really need you to think. Okay, what happens to the speed, wavelength, and frequency of a water wave when it moves from deeper end to a shallow end? So I want you to remember something. The velocity is actually given by frequency multiplied by the wavelength. When you move, okay, when you move a water wave, okay, from a deeper end to a shallow end, what you're going to expect is this: its speed will eventually reduce. Now, when it reduces, I want you to remember that velocity is actually directly proportional to the wavelength. Okay? So the more you increase the distance, the more you reduce the speed, the speed at which the person is going to travel. In other words, what I'm telling you is when you reduce the speed, you expect that even the wavelength is going to decrease or reduce. But what is going to remain constant in this case, remember, whenever you're doing variation, when you add the equal sign, you always add a constant, in this case, which is our frequency, then of course the wavelength. Now this wavelength, this frequency is actually constant. That implies that what is going to affect, what this velocity is going to affect is actually your wavelength, which is your distance, right? Then your frequency will not be affected. So in this case, what I'm trying to tell you is your velocity is going to reduce, your frequency is going to remain the same, your wavelength is also going to reduce. Okay? So speed should reduce, frequency should remain the same. So reduce should remain the same, and our answer is actually C. Let's see how interesting the next question is. Water waves were produced in a ripple tank using a vibrator frequency. Okay, so they've given us our frequency of 6 Hz. Then they say, which of the following values of speed and wavelength could the waves have? So we know that the speed is actually the frequency multiplied by the wavelength. Then here they're saying they've given us a wavelength of 6. So the first thing you're going to do is simply to put your 6 in the equation. Now, we'll be using, you can choose either to use your wavelength to test or your speed to test. So in this case, I'll be using wavelength. Let me use wavelength. If I put 6 here, if I put a 6 here, if I put a 6 where there is wavelength, is my velocity going to be 2? It can't. If I put a 2 where there is this wavelength, will my velocity be, will my speed be 4? No, it can't. If I put a 30 where there is wavelength, will my velocity or speed be equal to 10? No, it won't. So even this is wrong. How about if I put a 2 here? Will my speed of velocity be 12? Yes, it will. So this one is the answer. Okay. So in this case, our speed should equal to 12 centimeter per second. And then, of course, our wavelength is going to equal to 2 centimeters. Sound waves are being produced by radio loudspeakers, industrial machinery, and children in a playground. These sound waves have the same A same amplitude, B same frequency, C same speed, wavelength. I want you to imagine a scenario where you have 2 speakers. Okay? You have 2 speakers. You are standing here, right? This is speaker 1. And then this is going to be speaker 2. This speaker is producing a sound by your maps. This speaker is producing a sound by Chile 1. If you will be able to get the sounds at the same time, you're able to hear the sound which is being produced by your maps at the same time with the sound which is being produced by Chile 1. That implies that the 2 sounds are moving, okay, at the same speed. The sounds are moving at the same speed, but of course, one might of course be louder than the other, but the fact that you are hearing them at the same time, you are getting them at the same time, it means that they are moving at the same speed. What is going to be different is the amplitude. The amplitude will be different. Why? Because one might be louder than the other. Okay? The frequency is going to be different. Using the same concept I've given, one is going to be louder than the other. It's either the speakers, you might be hearing the speakers so much compared to the children. Okay? If you speaker, different, and everything. So it will be different, right? The wavelength will be different also. The fact that frequency and amplitude are different, your wavelength will also be different. But the fact that Mulefi Mfira Pamo, Abana Bale Punda in the background, and also the speakers, it implies that the 2 are moving at the same speed. Okay? So, your answer is they have the same speed. I want you to use this same concept. Okay? That's sound interference. The diagram shows reflection when light rays strike a rough surface. Now, I want you to look at what is happening. You have a ray of light which is coming in this direction. It hits. Okay? Whilst it hits, there is another ray of light which bounces up like that. This could have been a shiny surface. Okay? Okay, it's a rough surface, of course. But the fact that light is being projected upward means it's reflecting. It's a shiny surface because it is reflecting light, right? That is the analogy you should use. This light comes like this way. This wave of light comes like this. It bounces up. It goes upward. It gets reflected. I want you to see the disorganization which is happening here. Light rays are coming, others are going upward. Okay? Others are coming, others are going upward. What do you call this? This can't be angular reflection. Okay? This can't be parallel reflection. This can't be transparent. So the fact that they are moving in different directions, they are very disorganized. This is what we call diffuse reflection. Diffuse. In other words, you have this coming, this goes up. You have this coming, you have this going up. They are diffuse. Okay? In other words, they are moving everywhere. Okay? They are moving everywhere. You see? There's this guy going there. There's this guy going this side. Going this side. They are moving everywhere. So they are diffuse. Okay? The diagram shows a boy standing 3 meters away. So this guy is actually standing 3 meters. This is actually 3 meters away from a plane mirror. He then moves 1 meter close. So this guy now changes the location. He now moves at least 2 meters towards the mirror. I want you to think about something. If this is a plane mirror, then you are standing here, and then your distance from there to there is 2 meters. Your image which you are going to be seeing, it is going to be 2 meters near to you. Okay? If you check in a plane mirror, that's how it looks. If you stand like this, your reflection will be 2 meters away from you. In other words, the distance that you are covering from where the mirror is to where you are will be the same distance that the image will be away from the mirror on the other side. So since this guy moved 2 meters close to the mirror, the image is going to see is also going to be 2 meters away from the mirror. Okay? So if they say how far is he from his image, just add the 2. So 2 meters plus 2 meters. And then what you're going to have is going to be 4 meters. So our best answer is 4 meters. Which of the following is a characteristic of an image formed by a plane mirror? So of course this one is very simple. It can't be diminished. Plane mirrors don't produce diminished images. They can't be magnified. Of course, they can't be real. Okay? It is actually virtue. So this one is well known. Possibly to those that read, you'll be able to confirm with me. Which of the following best compares the magnetic properties of iron and steel? So you have iron, and then you have steel. Okay. When we say man of steel, I'm a man of steel, I'm a woman of steel, what does that mean? It simply means that your life, of course, might not be easy. Okay. It might not be soft. It might not be, it's not been straight like every other person. But that doesn't mean that when God blesses you, you become great. Because of the process that you have gone through, your success is going to remain permanent. Why? Because you underwent a very rough journey. Now, if you are a man of iron or you are a woman of iron, it simply means that your lifestyle is going to be very easy. Okay? Even the way you're going to acquire things, it will be easy. But eventually those things won't be lasting forever. They won't be permanent because you acquired them in a very suspicious and quick way. The same concept also. Iron is actually very easy to magnetize. Okay? It is very easy to magnetize, and that is why it makes temporal magnets. So, very easy to magnetize makes temporal magnets. Anyway, that's not the spin of a magnet. Let me, it's okay. Steel is not easy. It is actually very difficult to magnetize, but it makes permanent magnets. Okay? Difficult to magnetize, makes permanent magnets. For the sake of revision, makes permanent magnets. Okay. So the answer, of course, is D. The diagram shows two metal spheres R and S touching each other, placed on insulated stands. A negatively charged polythene rod is held near. So this is what is happening. You have this polythene rod, okay, which is negatively charged. you have R, then you have S. Okay, let me just do this. Let me remove the R from inside. You have R. Let me even wrap this so that I get a big circle. You have R. Let me just call this one R. This one is going to be S. Now, because this one is negatively charged, the rod is actually negatively charged. This one is neutral. All of them are neutral. When I say neutral, meaning they contain both positive and negative charges. So when you get the rod close to R, these negative charges will be repelled this side. Remember, like terms should repel, or like charges repel, and like charges attract. The positive charges will be attracted to this particular end. Okay? They will be attracted to this particular end. So eventually, because of repulsion, these will move. Okay? They will be attracted in the other sphere, and then eventually this sphere will remain what? Negative. Okay? This one will automatically remain positive. Okay? Have you seen what is happening? So one will remain positive, the other one will remain negative. So eventually R will be positive, the other one will be negative. Let me check for that answer. Okay, positive, negative. So C is our best answer. Just use the concept I've used. Okay, it's actually very simple. That's charging by conduction. A battery moves a charge of 70 coulombs. So we have a charge of 70 coulombs around the circuit at a constant rate in. So the time that we have is actually 1 minute, of which 1 minute we know that it is 60 seconds. Convert to seconds, please, not to minutes. What is the current which is going to be flowing? So of course current is represented by the letter I. But we know that charge is actually equal to IT. So our charge is going to equal to, what is the current? The current we don't know. So that's what we're finding. So we can make current the subject by simply dividing even this side. So our current is going to equal to our charge over our time. So current is going to equal to, what is charge? Charge is simply 70 coulombs over, what is our time? Our time is 60. So 70 divided by 60 is giving us 1.16. Okay, but because it is 666, this is going to be 1.17 amperes. Okay, that gives you your answer. So basically this is just going to be D. Two resistors of 12 ohms and 24 ohms are arranged in parallel. A 4 ampere current flows through a 12 resistor. What is the reading of current on the ammeter? So they want us to tell the reading of the current on this ammeter. But this is what I want you to know. For two resistors which are arranged in parallel, what is actually the same is actually their voltage. So the voltage which is going to go this side and the voltage which is also going to go this side are actually the same. Let me call voltage 1 and voltage 2. They will actually be the same. What is going to be different is simply the current. The current 1 and the current 2 which is going this side are actually going to be different. So we can use this guy. We can use what is complete to be able to calculate the current. So what we are going to do is this. We know that let me see, I said a 4 ampere current flows through this 12 ohm. Okay, so we know that velocity is equal to, sorry, let me just remove this. So we know that the velocity is actually equal to the current multiplied by your resistance. The resistance is simply the ability to prevent the flow of charge. Now, let's try to see the velocity, the voltage that we are going to find. I don't know why I love velocity, because I love kinematics a lot, distance time graphs, and the rest. So now from here, we can calculate the voltage. When we calculate the voltage, it will be very easy for us to calculate the current flowing in this side, because voltage is the same. So voltage is going to equal to, what is the current? They are saying it is 4 multiplied by, what is the resistor? It is the 12 resistor which this current is passing through. So 4 multiplied by 12, we are going to get the 48 volts. This 48 volts is the one which is passing here. It is also the one which is passing here. Meaning the voltage is the voltage which is going to this resistor, and the voltage which is going to this resistor are the same. Now, for this resistor here, we do not know the current, but we know that voltage is equal to IR. Now, mkwataka the voltage. Okay, voltage is the same kama resistor. What we don't know is the current, but the resistor we have, it is 24. So over 24. So ngamashita calculate current, what are you going to have? It's a 2.0 amperes. Now they're saying, what are you going to see here? So meaning you need to calculate the current for the whole thing. So the current which was going this side was 4 amperes. Then the one which is going this side is 2 amperes. Okay. So this is going to be 4 plus 2, which is going to give us 6 amperes. So this is what you're going to see on the ammeter. The diagram shows a coil in a magnetic diagram shows a coil in a magnet field. So I have a magnet field. So this, of course, is our south, this is our north. We have J and K. When the coil forms part of a DC motor, what must be connected to J and K? Okay, so for this one, you would want to constantly keep the coils rotating, right? You would want to constantly keep the coils rotating. So what you're going to put is actually a split ring, okay? Not an AC supply, no? Not a DC. So the best answers could have been slip ring or split ring. Now, because it's a DC motor, you'd want your coils to keep on rotating constantly without change over time. So what you would want to do is to put a split ring. Okay? To put a split ring, not a slip ring. A transformer is needed to convert mains 240 volts supply into a 6 volts supply. If there are 1000 turns on the primary coil, how many turns should there be on the secondary coil? So you start with the voltage. So your voltage primary is what they mentioned first, which is your 240 volts. Your voltage secondary is what they mentioned second, which is your 6 volts. Then, of course, your number of turns primary is what they mentioned first, which is the 1000. Then your number of turns secondary is what they want you to calculate. What is the formula you are going to be used? Of course, it's the voltage. Let me just start with the voltage. Okay, so of course it's voltage primary over voltage secondary equal to the number of turns primary over number of turns secondary. So what is the number of turns primary? Or let me just say the voltage primary was 240. And then voltage secondary was 6. Okay, the number of turns primary. Then what we are looking for is the number of turns secondary. So So this is going to be 6 multiplied by 1000, it will be 6000. 240 over 240. So the number of tens secondary, so 6000 divided by 240, which is going to be 25 tens secondary. So let's check. So this is the answer. Radon decays to polonium by emission of an alpha particle as shown by the following decay. So whenever you see alpha particle, let me give you this very important secret. Whenever you see alpha particle, think of helium. Or alpha decay, think of helium. Okay? By the following decay equation. So this is the decay equation that we have. Of course, it's producing an alpha, it's emitting an alpha particle. In this case, alpha particle I've mentioned, think of helium first. They're saying, what are the values of P and Q? So, you've seen polonium. On top there, they're saying this is this is 215. That is 215. And then down here you have 84. So you will be using helium to find the original, because helium is what polonium is emitting, right? Alpha particle. So you add the 4, because the 4 is on top, you add the 2. What you're going to get is X, which is going to have, let me see, 215. 215 plus 4. Okay, let me check properly what that number was. Sure, possibly maybe I could have missed it on the number, but this looks okay. This is 218. 218. So 218 plus 218 plus 4. 218 plus 4. This is going to have 222. And then 84 plus 2, this is going to be 86. So now you check, what are you going to have? This, your P is going to be 222, and then your Q is going to be something like 86. Okay, so the best answer is this one. Have you seen how simplified this is? Use the same concept also for your exam. An industry buys 200 grams of radioactive sample with a half-life of 5 years. How much of the radioactive sample will remain after 20 years? Let me show you how to solve this question. Very simple. The simplest way. They are saying it has a half-life of what? Okay, this radioactive sample has a half-life of 5 years, right? It has a half-life of 5 years. You want to know what is going to remain after 20 years. You will say 20 over 5 is going to give you 4 years. So you are going to be reducing these 200 grams 4 times and see what you're going to remain. So at initial, okay, let me just say, at 4 years, you have 200 grams. Okay. Then you reduce this. Let me see. 3 years, 100. 2 years. Sorry. So let me see, at 0, you're going to have, let me see, 200 grams. So you start with 0. Let's be log, I solved this. Start with 0 grams. At 1 year, you reduce. At 2 years, you reduce by half again, which is going to be something like 25. Sorry, 50. 3 years, 25. 4 years, 25 divided by 2, 12.5. So 4 times. So by the time it was 4 years, which is here, the material is going to be 12.5 grams. So you just start reducing from 0 until you reach your 4 years. If they said 5 years, we could have proceeded. 5 years, again, we reduce by half. So by 5 years, it could have been 2.5 kg. Okay, just like that. You just keep on reducing by half until you get your answer. We got to section B, which carried about 45 marks. Okay, so this one, let's see. Let me reduce my pen a bit. Figure B1.1 shows the main parts of measuring instruments found in a laboratory labeled A and B. Then they are saying, name the instrument labeled A. Of course, the instrument labeled A is simply a micrometer. This is a micrometer screw gauge. As a micrometer screw gauge, and the one labeled B is a vernier caliper. This is a vernier caliper. Which physical quantity is measured by instruments A and B? So, of course, they measure length. Which instrument is most suitable to measure the thickness of a razor blade? Whenever you want to measure thickness of something, use a micrometer screw gauge. Micrometer screw gauge. So which happens to be A. Please don't write the name of the instrument, just put A. Okay? This is just for the sake of revision, but make sure you put A, because they're saying which instrument is most suitable to measure the thickness of a razor blade. They didn't say name, they said which one. So it's between A and B. So it's actually your A. So this one is actually very simple. They just wanted to test you how good you are when it comes to instruments. We come to this particular question. They're saying figure B 2.1 shows a wooden ladder of length 4.5 meters inclined at a vertical height of 1.5. Then they're saying a ladder is used to pull a 900 suitcase by applying a force of 450 newtons. So first of all, let's write our data. So which one exactly is the distance of the effort and that of the load? So first of all, we have our effort to be 450 newtons, and then we have the weight of the crane, which is going to be that of the material that we are lifting, a wooden ladder, the material that we are pulling is about 900 newtons. So I want you to do what I'm doing. Just collect the data. Okay. That is a suitcase, right? So this is the weight of a suitcase. Okay. Let's recognize what we have. What else do we have? And then they're saying a vertical height of 1.5. So this is the distance or the length which is being covered by the suitcase or by the load, which is 1.5. So this is the distance of the load. Let me label it as distance of the load. So that's the distance of the load. Then this is the distance which is being covered by your effort. So this is the distance of the effort, which is 4.5. Of course, don't forget gravitational field force, which is 10 meters per second. 10 meters per second squared. And then they're saying, have we collected everything? Yes. They're saying we define a simple machine. So what is a simple machine? A simple machine is just a device which is used to make work easy by changing the direction of the force. I would say it's a device used to make work easy by changing the direction of force. That is a simple machine. Then they say calculate the velocity ratio. So velocity ratio is going to be given by the distance of the effort over the distance of the load. So let's check what is the distance of the effort. It is 4.5. The distance of the load is 1.5. So 4.5 divided by 1.5, 3. So our velocity ratio is going to be 3. It has no units. Then they say calculate the work done on the parking case against gravity. Okay? We know that work done is equal to force multiplied by distance. I already showed in the MCQ part, the multiple choice question part. So our force, they're saying calculate the work done on the parking case. So we're going to get the weight of the parking case. The weight of the parking case, which was 900. So it will be, so it's going to be 900 multiplied by 1.5. By the way, this is supposed to be work done. I don't know why I'm writing W just. So this is going to be 900 multiplied by 1.5. And then we're going to get 1350 joules. Okay? 1350 joules. That's work done. So many people actually make mistakes when it comes to forgetting units. Others forget the units. Others write wrong units, which is very, very much dangerous, because if you use the wrong units, it means you'll be marked wrong. Then they say we calculate the efficiency. So efficiency is equal to, you are putting in you'll be putting in what the machine is producing. Just a minute, where's my calculator? Okay, so efficiency. What is efficiency? Efficiency is basically how much work output your machine is giving out. Okay, how much work output your machine is actually giving out. So how do you calculate efficiency? Efficiency is just load over effort. Load over, that is how you're going to remember it. Efficiency is load over effort multiplied by 100. So let's try it. Load over effort. In other words, what I'm trying to tell you is, you are going to get your work done by the load. Okay, your work done by the load over work done by the effort. That's why we say load over effort. Okay, also the work done by the effort. So in this case, what do we have? Let me check. Do we have work done by the effort? No, we don't have. So let's try to calculate it. So work done by the effort is equal to, let's check, what was the effort? The effort was 450. It covered a distance of 4.5. So you do the same thing that you did there to calculate your 1350. So it will be 450 multiplied by 4.5. You are getting a 2025 joules, right? Then let's try to use the formula. So what we have is effort, the work done by the load first, over work done by the effort 1 week, then you multiply it by 100. So let's check 1350 divided by 2025. It's giving us 0.6666 multiplied by 100. We are getting 66.7%, which is just 67% if you round it to a whole number. So how do you remember efficiency? Efficiency is load over effort, but the work done by the load over the work done by the effort. That is how you find your efficiency. Okay. A crane lifts blocks through a vertical height. So let's first of all deduce our data. We've been given a height of 24 meters. The saying with a force is given to be 5,000 newtons at a constant speed of, the speed given is 6 meters per second. Then the time given is actually 4 seconds to reach the top building. How much work is done in getting the blocks to the top? Okay, so we will need to calculate our work done first. We know that work done is equal to force multiplied by distance. The same thing. Your force is actually 5,000. Your distance is actually 24 meters. So 5,000 multiplied by 24, you'll be getting 12. Let me just say 120,000. 120,000 joules. Okay. Then they say, okay, this is the work done, so you can put your 120,000. Don't forget the units, joules. Then the question continues by saying, what is the potential energy gained by the blocks? Let me see. Here they're saying, I want you to listen to the language. A crane lifts blocks through a vertical height of 24 meters with a force of 5,000 newtons, right? At a constant speed. At a constant speed. So, because the speed, okay, because we have a speed that is remained constant, the potential energy will actually remain the same. Okay? At a constant speed, your potential energy is equal to your work done. How? Potential energy is measured in joules. Work done is also measured in joules. When the speed is constant, your work done is actually equivalent to your potential energy. So in this case, your PE will still be 120,000 joules. Possibly the reason why they even give it 1 mark. So this is going to be 120,000 joules. Just have to think. Calculate the power developed by the blocks. We've been finding power. Power is equal to actually work done over your time. Of course, power is equal to work done is equal to force. And we've already calculated our work done, which was 120,000. Okay. So it's going to be 120,000 over the time just check. The time given was 4. So I get it something like 30,000. 30,000 watts. Okay, that is our power output. I can put my 30,000 here. Watts. Figure B 4.1 shows a graph of solid pure substance changing its state of matter as it is being heated. So you have a cooling curve here. And of course, this is your temperature. Of course, this is your time. So this is what I want you to notice. At 0, you have a solid, right? So what you have here is a solid. From A to B, the solid is actually melting. It's actually being heated. Okay, so here it is being heated. Okay, here it is actually being heated, right? Here it becomes liquid. Here it becomes liquid, but it's also boiling. Here it's a gas, very hot. Here it's a gas now going to vapor. Now the question is saying, what was the boiling point of the substance? So at what point exactly did it start boiling? It started boiling at this particular point. Okay, so at this particular point, here it's a liquid. Liquid it's very hot. Here you have a liquid. Sorry, I made a mistake. Here you have a liquid gas. How do I know? Because at this point it is boiling. It is boiling rapidly, right? At this point. So what is boiling? The liquid. And then while the liquid is boiling, what is it forming? Gas. Okay? So meaning, here, you have a solid which is going to turn into, at this point, you have a solid which is being heated, but it is now turning into a liquid. Here you have a liquid. Here you have a liquid which is going into becoming a gas. So now, it's now turning into a gas. So, what was the boiling point? The boiling, it started boiling when it was 40 degrees. Okay. At this point, that is when it started boiling. Okay. It's now started forming a gas. At which temperature will the substance exist both as a liquid and a gas? Liquid and gas is the same temperature. Okay? It's 40 degrees. State one difference between boiling and evaporation. So there's a difference between boiling and evaporation. Okay? Boiling occurs within the entire container. Okay? So boiling occurs within the entire container. Evaporation only affects surfaces. Evaporation occurs only at the surface. Evaporation occurs only at the surface of a liquid. boiling, okay, boiling occurs within the entire container, whilst evaporation only occurs on the surface of a liquid. Okay, that's evaporation. Evaporation only affects the surface of a liquid. Boiling is affecting the entire container of a liquid. What happens to heat supplied at points where there is no increase in temperature? So this one I want you to answer. To be homework, make sure you send the answer to 077766. Okay, sorry. 0777664046. I bet now I'm getting tired. It's tiring. Okay, so make sure you send me on my WhatsApp number. And of course, if you would want to register for tuitions, come for lessons at our academy, of course, HC Learning Academy, inbox me on this particular number on WhatsApp. I'll be able to respond to you. So you submit the last question to me. Let me give you a hint. You connect it to latent heat. That's the concept. Connect your theory, your thinking to latent heat and give me the answer. Figure B5.1 shows a wave with a frequency of 40 hertz. So let's have what we are. Well, let's see what we have. We have a frequency of 40 hertz. And then we have a distance, or let me say a wavelength, 1.5 meters. Define amplitude. Amplitude is simply the maximum displacement of a particle on a wave from its resting position. Okay, amplitude is the maximum amplitude is the maximum displacement of a particle on the wave. The maximum displacement of a particle on the wave from its resting or equilibrium position, from its resting position. Calculate the speed of the wave. Speed of the wave is equal to frequency multiplied by the wavelength. The frequency was 40 multiplied by the wavelength is 1.5. A wavelength is 1.5. So if you are calculating from this point, it will be from this point up to this point. If you are calculating from this point, it will be from that point to that point. That is how you calculate your wavelength. Whatever point you pick, so the same to the next. So let's see what we're going to have. There is 40 multiplied by 1.5, which is going to be 60. Meters per second. So this is going to be 60 meters per second. Okay, find the period of the wave. So we know that period is actually 1 over frequency. Period is actually 1 over, what's the frequency? Our frequency given is 40 hertz. So you're going to put your 40 here. And of course, your period is going to equal to 1 divided by 40. It's going to be 0.025 seconds. Okay, so this is where we are going to end. Make sure you subscribe to this YouTube channel so that in the next phase, the next lesson that I will be solving, you will be able to follow up in the next phase where we are supposed to graph and eventually be able to solve as many questions as we can. I'll be able to show you how to graph, how to be able to come up with your distance time graph under kinematics in the next video session. If you found this video interesting and helpful, consider subscribing, hitting the like button, and don't forget to share to others. Thank you so much.